Somewhere in our galaxy, about 6,000 light-years from where you're sitting right now, there is a star that should not exist. Not in the way that sounds poetic. In the way that means physicists have looked at the data, run the models, checked their math 3 times, and come back with the same answer. This is impossible. And yet, there it is. Burning. Spinning. Defying everything we thought we understood about how stars are born, how they die, and what the absolute physical limits of matter in this universe actually are. For decades, we dismissed objects like this as outliers, measurement errors, theoretical curiosities. But the more we look, the more we find them. And what they're telling us about the universe is either going to rewrite astrophysics or expose a crack in physics so deep that nothing we currently believe can be fully trusted. We're talking about ultra-massive stars. And the story of how they broke our understanding of the universe starts with something that sounds completely ordinary. A stellar nursery. Stars are born in clouds. Enormous, cold, dark regions of gas and dust called molecular clouds, some of them stretching hundreds of light-years across. Gravity pulls regions of these clouds inward. The gas collapses, heats up, and eventually ignites nuclear fusion. A star is born. Simple enough. We've understood the basics of this process for the better part of a century. But there is a rule, a hard limit baked into the physics of stars themselves. It's called the Eddington limit, named after the British astrophysicist Arthur Eddington, who first described it in the early 20th century. Here is the idea. As a star gets more massive, it burns hotter and brighter. That light carries energy, and energy carries pressure. Radiation pressure pushes outward on the surrounding gas, while gravity pulls inward. At a certain mass, the outward radiation pressure from the star's own light becomes so intense that it overcomes the inward pull of gravity. The star starts blowing itself apart. It can no longer accrete new material. It cannot grow. Based on this principle, the theoretical upper mass limit for a star was calculated to be somewhere around 150 times the mass of our Sun. Maybe 200 times under very specific conditions. That was the ceiling. That was the wall. Everything above that was supposed to be physically impossible. Then we found R136A1. Located in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, R136A1 sits at the center of an extraordinarily dense star cluster called R136, inside a turbulent star-forming region known as the Tarantula Nebula. When astronomers first began studying this cluster in detail using the Hubble Space Telescope and later the Very Large Telescope in Chile, they knew they were looking at something extreme. But the numbers that came back were stunning. R136A1 has a mass estimated at around 200 to 300 times the mass of our Sun. Some measurements have pushed that estimate even higher. It is, by every metric we have, the most massive star ever confirmed in the observable universe. And it breaks the Eddington limit clean in half. How does it exist? The honest answer is that we are not entirely sure. One leading theory involves the conditions in R136 itself. This cluster is so extraordinarily dense, packing hundreds of massive stars into a region only a few light-years across, that the environment in which R136A1 formed was unlike almost anywhere else in the modern universe. Some researchers believe that in the chaotic early stages of the cluster's formation, protostars collided and merged before they had fully ignited. If enough of these stellar embryos crashed together fast enough before radiation pressure had a chance to build up and stop the process, the result could be a single object that punched straight through the Eddington ceiling. Not because the physics was wrong, because the physics never had time to kick in. There's another possibility. R136A1 may not have formed from a single collapse at all, but from the sequential merger of already formed massive stars later in the cluster's life. Simulations show that in environments as dense as R136, close gravitational encounters between stars happen constantly. Stars get flung inward, spiral together, and merge. Each merger adds mass. Each addition of mass pushes the star's luminosity higher, flooding its outer layers with radiation, causing it to shed enormous quantities of material through stellar winds. R136A1 is estimated to be losing mass equivalent to the entire Earth's mass every single month. It is simultaneously one of the most massive objects and one of the most violently self-destructive objects in the known universe. And here is where it gets deeply unsettling. R136A1 is not young anymore. It's already middle-aged by stellar standards. Estimates put it at roughly 1 to 2 million years old, which sounds ancient, but for a star this massive is practically infancy. Stars at this mass level burn through their nuclear fuel so ferociously that their entire lifespan fits inside a few million years. For context, our Sun has been burning for 4.6 billion years and has another 5 billion to go. R136A1 may have only a few 100,000 years left, maybe less. When it dies, the explosion will be unlike anything in our immediate cosmic neighborhood. Not a standard supernova. Something called a pair instability supernova. An event so energetic that instead of leaving behind a neutron star or a black hole, the explosion tears the star completely apart. No remnant, no core. Nothing left but an expanding shell of heavy elements ripping through space at thousands of kilometers per second. The entire star, all hundreds of solar masses of it, converted almost entirely into raw energy and dispersed across the galaxy. But R136A1 is only part of the story. Because once astronomers started looking carefully, they found more of these objects. Not many, but enough. Stars at 150 solar masses, 200 possibly higher, lurking in the densest clusters in the local universe. And each discovery forces the same uncomfortable recalibration. The Eddington limit is not exactly wrong. The physics behind it is solid, but it describes an equilibrium, a steady-state balance between radiation and gravity. What these stars reveal is that nature doesn't always wait for equilibrium. Under the right conditions, in environments violent and dense enough, matter accumulates faster than the rules can stop it. That realization has profound implications not just for stellar physics but for cosmology. Because the early universe, in its first few 100 million years, was almost nothing but those conditions. Dense, hot, violent beyond anything that exists today. If ultramassive stars form readily in dense modern clusters, they almost certainly formed in enormous numbers in the early universe. And ultramassive stars, when they die, seed their surroundings with heavy elements. Carbon, oxygen, iron, all of the ingredients for planets, for chemistry, for life. If the first generation of stars were far more massive than our models assumed, then the early enrichment of the universe with heavy elements happened faster and more dramatically than we calculated. That changes the timeline. It changes the conditions for the first galaxies. It changes, potentially, the conditions under which life became possible anywhere in the cosmos. The James Webb Space Telescope, now returning data that is genuinely reshaping early universe astronomy, has been finding galaxies in the very early universe that are far more massive, far more chemically enriched, and far more structured than our models predicted they should be at that age. Some researchers believe that ultramassive stars are part of the explanation, that the universe's early period of star formation was more extreme, more intense, and more consequential than any of our simulations had suggested. We built our models of the cosmos on assumptions about what stars can and cannot be. Those assumptions felt secure. They were mathematically grounded, observationally supported, and held up for generations. R136A1 and the growing family of stars like it are telling us those assumptions had a ceiling we didn't know about. And above that ceiling, the universe has been doing things we never predicted, in ways we don't fully understand, for longer than we've been paying attention. The star that cannot exist, exists. And now we have to figure out what else we got wrong.